can go into multivariate regressions, but before we get into multivariate regression, what is the variance in error? So what is left to be gained is the variance of error. First thing is, how do I know that this method is right, this model is right? Remember, suppose somebody gave you data, which is what the usually case, you fit your linear regression. Now when should I be happy about it? I fit linear regression, I have got beta naught and beta 1, you can give a data, you fit a linear regression model. How do I know that okay, this model is linear regression, or should I go for a better model? Like I told you, whether noise, which assumption is violated, how will I know? If all the assumptions are obeyed, then you know that the model is good, but how do I know which assumptions are violated, or how do I know that the assumptions are obeyed? You have a set of assumptions, right, that has to be validated so that your model is, you can say that linear regression model is the best model for this data. You understand my question? Somebody gave you y and x, you fit a linear model, loss function can it be ever 0? Your noise is there, loss function can never be 0, your noise is there. This is the problem, nobody can get 0 error, error will always be there, residual will always be there. Then what do? We test for residuals. So noise cannot be 0, residuals cannot be 0, and therefore we have to check the assumptions that we made using the residuals. So if you have fit, if the truth is linear and you have fit a good linear model, what should be the residuals? What is the assumption about noise? Normal 0, sigma square, homoscedastic. So the same way residual should also be normally distributed, because if you would have fit everything correctly, what should be left out? What have we not modeled? We have not modeled the noise. And what is the assumption about noise? Gaussian IID 0, sigma square, keep that in mind, Gaussian IID 0, sigma square. All of this, the residual has to obey all of this. So we are going to check for the residuals. What is the residuals? Y minus y hat. So y minus y hat is my residual. So I am going to check for constant variance, I am going to check for normal distribution, I am going to check for independence, and I am even going to check for linearity assumption. These are the assumptions I made. So this is why it is very important to know the assumptions. These are the assumptions I made about the truth, and if my model is right, all this assumption should be obeyed. Okay. So we can just do it graphically. Okay. So if you plot the residuals versus x, how should it be? If you plot residuals versus x, how should it be? Will there be a residual relation between residual and x? Will there be a relation between residual and x? Did we assume any relation between noise and x? What did we say about x? Noise IID. So it is independent, and noise and input are unrelated. So there should be no relation between residual and x. So if you plot it, they should look like independent, and there should be no linear or non-linear relationship. So if you have this kind of relationship, then you know that y is not equals to mx, but there is a curvilinear relationship happening, there is a quadratic relationship. Simple plot of residual versus x should give you lot more information, right. You see that it is curvilinear, it is not independent, and it is not flat, it is having a relationship. So the simple plot of residual versus x should tell you whether you have did a good model or not. Okay. And non-constant variance, if you plot again residual versus x, the variance should remain constant. If it is going wider, then you know that you have to fit a heteroscedastic model, your linear regression model is not right, you have to fit a heteroscedastic model. In the previous case you have to fit a non-linear model, in this case you have to fit a heteroscedastic model. And if you have this kind of oscillatory output residual versus x, then you know that there is no independence relationship is violated. Probably noise is not independent and therefore you have to fit a noise model. Okay. Just by plotting the residuals as a function of x, you will be able to have a lot more understanding, whether you want to fit a heteroscedastic model, whether you want to fit a noise model, or whether you want to go for non-linear models. If you do not do this analysis and blindly use non-linear model, you will not solve the problem, you will not get a better model, because in this case you have to fit a noise model. It is not the linearity which is problem, it is the noise model which is the problem. Okay. So that is where the analysis becomes very useful. I do not think so any of you would have done this analysis when you fit a linear regression. You would have simply fit the linear regression hoping it will, if it does not you would have gone for a non-linear or something model, but this is the analysis one has to do. These are the assumptions we make, and of course we can also check for probability plot of residuals to assume whether it is Gaussian or non-Gaussian. Remember we have learnt about probability plots, I think I have asked in your quiz 1 as well. So probability plots should help me get you whether it is Gaussian or non-Gaussian. So that way we check all the assumptions on the noise, is it following, the residuals follow the same. If every assumption is followed, then you say okay, my linear regression model is good. Okay. So that is what this least squares has to take with. Make sense? Clear? So now not only we use that, you will see that there is something called as R square statistic, okay, which is very widely used, that explains what is the fit, how much is the fit, and that statistic also says that statistic simply is a function of how much variability in y is explained by x, how much variability in y is explained by x, typically like your ANOVA. ANOVA also we do the same, right. So the same here, but we are now getting into formal details, like we have derived it completely. So now we look at residual sum square. We know residual is y minus y hat. So residual sum square is summation of y minus y hat the whole square, which is just the loss function without the n value. Okay. This is residual sum square, and we know what is the total sum square. We know what is the total sum square, right. Total sum square is what? Y minus y bar the whole square, that is the total variation in the data. Residual is what? Y minus y hat the whole square. Okay. Y minus y hat the whole square is residual squared, and y minus y bar is the total variation in the data around the mean value. So now what is R square is simply nothing but the variability explained by x, the variability explained by x, the variability of y explained by x, that is what you fit a model, right, y equals to beta 1 x plus beta naught. So we are saying what is the variability explained by the model, in fact beta naught is also included. So you can say what is the variability explained by the model. The variability explained by the model is what? Total sum squared minus RSS. What is total sum squared minus residual? That is the variability explained by the model divided by total, that gives you the percentage of variability explained by into 100, gives you the percentage of variability explained by the model. That is what is R square. You will see that R square statistic in every book, not only in books, every model, every when you develop, when you use code, MATLAB or Python softwares, what it simply R square is the into R square into 100 is nothing but the percentage of variability in y, percentage of variability of y explained by the model. If it is 95, that means 95% of the data is explained by your model. If it is 50, you know that you have lost, meaning only 50% is explained by your model. Then what is it? You may want to fit another model, a non-linear model, right. So this is what R square statistic is. Clear? R square statistic is simply the R square into 100 is nothing but the percentage of variance, variability in y explained by the model, explained by the linear model, that is nothing but total sum square. What is the percentage of variability? Explain. Total sum square minus residual sum square divided by total sum square is the ratio, and into 100 is nothing but percentage of variability of y explained by your x, your model basically. Now the total is reduced by residual. So remember, what is TSS minus RSS? Total minus residual. So TSS minus RSS is the explained variation, right. So this is my explained variation divided by total variation, right. So what should be this number? If RSS is 0, what does it mean? 1. If RSS is 0, what does it mean? My model has completely explained by the data, that is what. So the lower the RSS, the better it is, which is what makes sense. That means the lower the unexplained variability, that means the lower the residual. That is what you are alluding to. You said residual should be 0, right. If residual is 0, your R square is 1, and percentage variability R square into 100 percentage is 100%, but you will never get R square to be 1 unless you make up the data, okay. So this is going to be close to 1, the closer to the 1 the better it is, clear. So that completes our, I have not derived confidence intervals for, okay, what I call the confidence intervals for the parameters, okay, we will not do that, okay. We will understand R squares and move on. There are confidence intervals for parameters, it will follow a t-square, t distribution, etc. Okay, I will not delve deeper into that. So the next class, tomorrow's class, we will talk about what is adjusted R square, okay, that is simple, and then we move on to multivariate linear regression and logistic regression.